OK, cool. Thanks. Let's get this started. So as you can see, the name of my talk was getting started with 3.js and WebGL, but I had this thought. Are you familiar with this drawing? So I had this impression that everything that's kind of getting started, it's like, OK, I'm done. I've got a spinning cube. What do I do now? So it's going to be actually like, OK, getting things done with 3.js and WebGL, and hopefully we can get to that. So we're going to do some unit testing first to check that the talk is actually working. So I'm here. Yes, I am. The audience is here. OK, so checks out. This is my cat contribution. So it's Nyan Cat. So yeah, this is WebGL. So we're done. That's it. That's WebGL. That's a cat. So it cannot get any better. It cannot get any better than this. So yeah, as Karina said, I work for BeReal. We're a production company, creative partner that we've done several things on the internet, like the first WebGL game that was for Google Maps, or the Wilderness Downtown, first HTML5 video clip for Arcade Fire, or the Gravity website. So yeah, we do this kind of cool things. So if you're interested in creative career, ask me. And on my personal time, I do all these kind of explorations on graphics and everything that can run on the web, because I'm really fascinated by the web platform and JavaScript. I love it. And this is part of many of my experiments. So how do you get to build 3D experiences? What do we understand as building 3D experiences? So I'm going to show you something that I've been working lately. I finished a few months ago. I'm going to play it. It's this. It's a little bit blurry. Let me try again with the high quality setting directly. So this is running on the browser. It's using WebGL, and like you can actually go in interactive and look around. This is all being rendered in real time on your browser. So it's pretty powerful. So it might look like a video, but it's actually running on real time. It's making use of a web API. You can see it here that it's actually running on a browser. It's not a video, it's interactive. So how do you get to build something like this? So we're using WebGL. WebGL, it's a web API. It's controlled by the Kronos group. You can get these links here to check. You've got all the documentation on the Mozilla Developer Network or on the Microsoft Developer Network. There are many samples, and there's many Chrome experiments. And basically, it's an API. It's a JavaScript API that allows us to harness the power of the GPUs that are running on our systems. It's based on OpenGL ES, which is the one that runs on your mobile devices, not the one that runs on desktops. So it's a bit limited regarding of the current state-of-the-art OpenGL, but it gets a lot of things done. So it's really useful. So the thing with WebGL is that demo like this is one of the St. Angeles Observatory, one of the classic sample demos. If you check the code, it's a crazy amount of code binding buffers, getting data from one end to the other, because everything that's on your main CPU memory has to be transferred to the GPU memory, so it works much faster. So it gets pretty verbose and pretty complicated. So we have 3.js. It's a higher-level JavaScript API. It's a layer of abstraction on top of all these elements that you have for WebGL. Again, 3.js.org, it's the main site for the project. You've got the GitHub page with everything. There's examples, there's documentation, there's even a getting started guide with everything that you need. So it's designed for, it's conceptualized for beginners. So it's for people that want to do cool things on the browser without actually lots of 3D algebra knowledge. And it really works for that purpose. So how do you start it? So you have to set up. You've seen a bit of this before on the previous talk with about WebGL. So basically, your code structure is you utilize your renderer, then you set up your scene, and then you just run through the animation loop. That's basically everything you have to do. So this would be the code. You've seen something similar before. You include the library, and then you create a renderer. This is a new thing. You set the pixel ratio because now we're dealing with retina displays, high device density screens. You set the size because you want to cover the whole screen or part of the screen. Attach it to your DOM. Create a scene. A scene, sorry, it's a container for everything that we want to draw. So that scene, it's basically structured so we can do a few optimizations. It basically holds everything in our world, and when you put a camera on it, then we can discriminate what's going to be drawn depending on what the camera is looking. So everything that's, for instance, behind us, it doesn't get computed. So it's kind of these optimizations. Then we create a camera based on an aspect ratio. It's more or less modeling a real little camera. So you've got the size, the field of view, the distance that you want to look at. And set the render loop. Basically, we request animation frame and call the renderer with our scene and our camera. You can have many scenes, you can have many cameras, and you can kind of combine them to get a more complex rendering experience. So what do we do with the scene? We need to add some stuff to render. Stuff, it's usually objects. We call them meshes. A mesh, it's a combination of a geometry and a material. So we basically created with the 3-mesh object. We provide the geometry, we provide the material, add it to our scene, and then we can render it. So how do we choose a geometry? So there's a few three.js primitives. There's sphere, boxes, cylinders, towards geometry. And it's basically like this. So you can create it. Keep in mind this representation. This is like the most basic material you can use. It's a wireframe mesh. But all these different points connected by lines are going to be important later. So how do you use this? You can basically create a material. And then, for instance, a cube, it's a new 3-mesh with a box geometry, specifying the size, width, height, depth. Add it to the scene. You can create a sphere. For instance, it's icosahedron geometry. It's all pretty much the same thing. You create a geometry with your parameters. You place it on the world, you add it to your scene, the renderer is going to take care of that. So another way of providing a geometry, besides these constructors, these constructors that come by default, it's loading models, loading objects that are created with Maya, 3D Studio, in many different formats. So for instance, this is Edward Snowden sculpture, the one that was retired, it was forbidden to be on Green Park, I think it was. And someone posted the STL file on the internet, so you can use it, and basically you can load it really easily. So loading a model, same thing. It's basically you instantiate an object loader or an STL loader, depending on the format that you're going to be using. Provide the file you want to load, and you've got an asynchronous callback with the geometry. So again, you create your mesh with a geometry material, put it on your scene. It's to get taken care of. So once you have something running on your you've got geometry, you've got a mesh, you have to choose how to lead it, because that's how things look more realistic. So there's the light model. That's basically what defines how a material is going to look. So basically, there's flat, there's a very basic Lambert and Phong. Let's get back to this one, and what we're going to do is, this is called mesh normal material. It shows what's the normal direction of each surface. Basically, the normal, it's the direction in which a face is looking. So this face is looking up, this face is looking down. It's used for illumination. So you know the surface that is looking up, it's going to be lit by these lights, and if one is looking down, it's not going to be as much lit. So we use that for calculations. So for instance, if we do, we have a function called create Phong material. Can I do this? Cool. So this function basically, can you read correctly? Like this? OK. So this creates a mesh form material. And the constructor has a few variables, like you can specify a color that you want the surface to be. You can specify a normal map, which defines like the details of the surface, and a few other things. So if I take my Snowden model, and I say that the material, which is part of my mesh, it's this create form material, we're going to get this different. I actually need to tell the geometry that the normals need update, small detail. So now we have this. And then we have a certain number of lights. We have an ambient light that defines like the global term, like how it looks. Right now, the ambient light, it's got a color. It's this kind of gray, but I could set an RGB, so it's, let's say, just a bit red. So that's what defines the whole color. And I also have an overhead white light, which you can see here. And I can do all kinds of things with these materials. These are the default materials that you can play with them. For instance, if I take my Snowden.material, it's got, I don't know, like shininess. Right now it's a value of 30, but if I put it to 100, it's way shinier. You can see that it looks more like plastic. If I crank it up to 500, it looks really porcelain looking. So that's basically the values that you're going to be playing with. You can do lots of stuff with this. So how do you add all these things together? So then when we have chosen one of our light model materials, like Lambert or Phong material, we have to add some lights. So we have also three.js has a lot of different lights. We have an ambient light, which is the diffuse term. We have the directional light. Same thing, you just create it, specify the data on the constructor, place it on the scene, and add it. And the renderer is going to take all that exists in the scene, calculate correctly, and render it to the screen. So there's also a spotlight, which behaves more like this kind of light cannons. Some of the lights with some of the materials can have shadow, like cast shadows. So you have to play with all this. That's what it comes with by default. But there's other kind of lighting models that you can use. Like, for instance, there's a spherical environment mapping. This one, it's much better. It's using circular texture, and what it does is creates a much nicer lighting just by using a texture, actually. So the texture is something like this. Let me see 1 second. It's this one. So this is the texture you're using, and you can replace it. So it's much easier to define a lighting model with Photoshop and then bring it into your scene than having all the calculations. So there's another one, which is the image-based lighting. This one uses an environment, like a cube map or any rectangular panorama, like street view. And then you get like much nicer, it's a bit dark, actually, but you get much nicer materials. You can see that this one has all these much nicer reflections on the back and lights. And if you just change the surroundings, it just goes, it just looks as if it was there. So another way of choosing a lighting model is just not caring about lighting models and using baked textures. So in the demo in Cruciform that you've seen before, this is actually the wall lights. It's just a big texture, a big dark texture actually. But like, for instance, that's the ground, and that's the sides of the wall. That's the lights from the ceiling. So basically, you texture all these lights, and you don't have to worry. Because mostly, like the diffuse term in an environment, it doesn't change. It doesn't change with your view. What changes is the specular term, and that's the thing that you have to care when you want to code it. So basically, that's what you have. Like everything, it's all these light models are actually running on shaders, are running on the GPU. So shaders, it's more like a more complicated concept for this talk, but I'll try to explain it. Basically, a shader is a program that tells the system how to draw something on screen. So we have two kinds of shaders. We have vertex shaders, and we have, sorry, 1 second, okay. We have vertex shaders, and we have fragment shaders. The vertex shader defines how a geometry has to be transformed, like how something, all the points that we've seen go into screen, and a fragment shader defines how things are drawn, like what color goes into each pixel. So you can, for instance, let's see, which program is this one? Yeah, so let's say that we have this scene here, and we want to see just the, wait a second, okay, much better. So, okay. So, like this is our fragment shader, and then this is what, it's not entirely JavaScript. This is just GLSL. So that's something that you provide to the material, and you have to code. It's kind of a C dialect. So for instance, we can do like, let's make the color it's just an orange color. Okay, back free. Okay, sorry. So this is kind of like coding. So I've just turned everything into a purple color. I could use, for instance, just the diffuse, like the diffuse texture, is it? Diffuse? No. Yeah, so this is just the flat. You see, this is the flat image. I can check the specular, for instance. So these are all textures that I've uploaded, I've specified to the material, and then in the fragment shader, I define how I want them to play. I can use, for instance, the environment mapping, which is like this, so everything looks like it's a mirror. And basically what you do on the fragment shader is just take all these different textures, different computer values, and turn them into a texture that looks right on screen. Okay. So there's been lots of talks about Shader Toy. So if you haven't seen it, it's plays with that. It's a website that you can use to code your shaders, running them on the browser. Everything is running on just 2 triangles, so it's pretty amazing. You can do, let me see one thing. This, for instance, this one. So this one is creating a sea landscape, and it's playing music using the GPU. And basically, all this scene that you're seeing, there's little no textures. There's no moon, for instance. That's no moon. And everything is being rendered with this equation. Everything is a mathematical equation, and it's being rendered for each pixel on screen. So each pixel defines how it looks in that scene, with the reflection, with the water, with the sky, the clouds, everything. It's pretty awesome. So check it out, shadertoy.com. So once we have everything, we have our objects, our meshes with our materials, our lights, everything, how we do get to animate that? So everything, it's a 3D object. That's kind of the prototype of everything on three.js. Can be translated, can be rotated, can be scaled. Okay. And what you do basically, it's in your code, in your JavaScript code, just take a cube, set position. It's 3 values in 3D, X, Y, Z. You can you can address one of the components. You can change the rotation. You can set the whole rotation. You can move the camera to a specific point a long time. You can create a new position and make the camera look at that position. So that's how you're going to be moving everything and telling how things move. You would be using probably an animation library. You would be using a twinning library, or reading from some scene file telling you how the camera moves, how everything moves. Or you would be using controls, like you've seen on the WebGL. There's a long set of different controls that connect the input with the camera in the scene. There's the traditional orbit controls, in which you kind of rotate around an object in your scene. Or there's the VR controls, which connect with a VR HMD. There's device orientation controls in case you're developing for cardboard, so it uses the accelerometer on your phone. And basically, on your render loop, you just use controls update, and then the camera would be on the right orientation. Good. So when you're doing all this, the thing is that it's difficult to get right, because this is basically something that I kind of advise to discover as a hobby. That's not like getting into game development like crazy. So when you're exploring this, it's okay to not go straight for something that you want to do. It's okay to kind of digress. It's okay to procrastinate, because usually you get things out of procrastinating, at least in my case. So for instance, while doing that demo, I was researching the parallax-corrected reflection mapping, which is what makes the walls look kind of glossy and everything's corrected. But then I wanted to investigate a bit more about materials, so I went for a long hike trying to understand materials with the physical-based rendering. So it was for a long time doing weird things, like trying to replicate the bull. So that's the real one, that's the WebGL one, still far from perfect, but weird things that happen. Then you start doing more things, more materials. You get into crazy stuff, like placing faces on your geometry. What is this? I don't know. So, so also like trying to get this for the camera work, I came up with a library that it's like a storyboard. There's lots of solutions for timelines, but for instance, I came with this one that it's something that you can define with a JSON, and just with like regular human language, you can define all the animation for this. This is on GitHub, of course. It's pretty useful. If someone wants to build like a timeline editor on top of that, I'd be perfectly okay with that. Another thing that you get by the end when it's running, it's post-processing. That's a really important part of what we consider the final CGI look. I've been working on a library for post-processing for three.js. It's called Wagner. Three.js has its own post-processing system, but I don't really like it. I don't think it's clear enough, so I came up with a simpler one. This, for instance, is scene running with the post-processing. It's got all the depth of field. It's got lights. It's got a bit of dirty on the lens, like all the cool stuff that they're doing on the games. And it's pretty easy to use. So you basically include the files and create a composer that's depending on your renderer. Set the size that you want to have, so it has to match the size of your renderer. And basically, instead of calling render scene, you just reset the composer, tell the composer to render that scene, so it holds it on a frame buffer, and then you put it on screen. That's the most basic. Doing that would basically do the same as rendering a scene. So that's the funny thing. So this would be like your scene. This got nothing on it. Then you create a CGA pass, for instance, to simulate a CGA display. And on your render, you do the composer reset, render, then execute the pass that's going to do this CGA look, and then to screen. So what you get, it's something like this. So you're processing all the pixels on your buffer to look like an old CGA for colors display. So most passes that you cannot never go wrong with, it's depth of field. That looks really nice. Don't overdo it. That's the secret for everything. A bloom, which makes things kind of glare, like things that look very bright. Chromatic aberration, it's something that photographers or cinematographers try to get away from, but in CGI, we just do flares and chromatic aberration, all things that shouldn't be done. Tone mapping, it's super nice, so you get the exact tone that you want. Everyone is doing it on movies, on TV shows. A vignette, which makes like this sense of the borders are darker. Noise, it's interesting that we want to have the best looking CGI image, but actually adding noise makes it more real in our eyes. So basically the secret is not to not overdo it. Like everything has to be subtle. So we know as developers that when we have something, we want to show it, but like subtlety, it's the key with this kind of effects. So when you're doing all this, it's difficult to actually like how do you debug, how you optimize all this. There's this one library I made because if you're working with shaders and usually, let me see 1 second. So basically, if you've got an error, like let's try again. You're okay. What's this? Okay, wait. What? Where? Man. Oh no. This. Okay. It couldn't compile. So it's pretty, like every time you break the shader, it's something like this. It's pretty annoying to find. So this library I made that you can install with NPM, it's called Augmented compile shader. What it does, it takes the WebGL compile shader, which takes this source code and validates it, and in case there's something wrong, what it does is basically put this on screen, which is much easier for you to see, okay, I screw up with there's no precision specified for float, so go back to the code. It's a kind of nice library. Based on the same concept of augmenting the prototypes or taking objects from native browser and turn it into something much better. There's this other library I did. Usually when you have something on three.js, like let's say you've got the cube and you check on the console, you see this kind of structures, and you open it, it's kind of weird, and the matrix, it's got elements. Okay, you don't know how to read that. So basically what I do is I trap console.log, and if I recognize some of the type of the objects that are being passed, what I do is use a different rendering system. Like for instance, in this case, I'm using a table. So you can actually format much correctly everything that you want to debug. So if you have any object that you know how it should be structured on the console, with that system, which is hooking into console.log and modifying the output depending on your inputs, you can do things like that. Or you can do even things like, let's say that you want to see how's the materials. So yeah, you can render graphics on the console. So that's pretty cool. Yeah, it's pretty fun because you can start doing lots of things. You can do an animated GIF, so you can output an animated GIF out of your console log. Cool. So another thing, you've probably seen it, there's the WebGL shader editor. This is something also I've been working. It's, I mean, it's basically, there's already a shader editor for Firefox. This one's for Chrome. So basically, you can play with it, check everything, see what's this. OK, I'm going to modify this, and I'm going to come to the vertex shader, and I'm going to say, like, so the position of my vertex, it's going to be like this. Cool. OK, this renders. And then post dot, I don't know, z, it's going to be multiplied by the sinus of the y. So OK, I don't know what I did. So time 0. Let's see. Oh, this is a lot. OK. Let's see. OK. OK, I just completely destroyed Edward Snowden. Let's see, 0.5, something better. OK, this is see, I mean, but it's cool because then you can play with everything on the browser. It's a much faster process. And then of course you can also modify your shaders here, and same thing, modify everything. It's a pretty cool process. It's very difficult to debug on the actual GPU code, so that's the best that you can kind of get. Okay, opa. Shit, did I completely? What do I do? 1 second. Shit. What? OK, there we go. OK, so that's it. So releasing. Once you've got all this done, so there's a few considerations before doing that. There's many platforms. So WebGL is now pretty standardized, but it's running on desktop, it's running on laptops, it's running on mobile phones, on iOS 8 now. So you have to consider for that. You have to consider for instance, Windows has a different kind of a bit more stickler implementation of WebGL. There's Retina displays, which are massive, considering the number of pixels that you're drawing. So usually you might have to consider that you have to downsize your textures. You might have to simplify models, making them lower resolution. You may have to scale down the actual render and then stretch it back. Or you might have to reduce completely or just modify the post-processing. All these kinds are kind of intensive. Use a CDN like Cloudflare, because usually when we're doing all these things, there's like models and textures are pretty big. But if you're at that point releasing something, congratulations, that's the whole thing. Everything that is released is a good release. And I've got time for lessons learned. Release early, release often. It's pretty much, everyone says the same, but if you're trying to do something out of a hobby, don't obsess like it's not going to be perfect. So go for whatever you think it can be done. If you are hitting a wall, forget about it for a while, go do something else. Remember, there's creation through procrastination, or it's also called yak shaving. But you can come back at a later time, and you might have learned a new thing that unlocks that thing that you wanted to do. And slowly you will be able to be doing anything you want, like medical visualizations or games or web VR. So again, all this has to be iterated, and then iterate it again. Try to block as soon as possible. Try to place every object, like as many things on your scene. That's super important for WebVR. But basically, try to get everything there and then refine. So it's a bit like the progressive enhancement. You have to first know what's your scene going to contain, and then build from that. Keep the music for last if you're using music, because you're going to hear it 1,000 times. You're going to end up hating it. Or even better, try to use a different music for the final release. And do what I call the performance-driven development, which is basically every change you do, make sure it works on all your target platforms before going on for a while, because maybe you got to a point in which you cannot go back trying to improve the performance. It's not like something that, if it's going slow on a different platform, it's not like something easy to fix. It's probably going to give you a lot of misery. And as long as it works, it's fine. I mean, that's the trick. It doesn't have to be technically perfect. It doesn't have to be mathematically correct. It has to work, and it has to look nice. So that's me. I work as technical director in creative technologies at BeReal. I've got my website, creativereals.com. I'm going to show you some things that also can be done, like shiny spheres that bounce around, or spheres that follow each other in kind of a popcorn dance. I don't know. That's what your imagination can come up to create. You can add physics. You can add all kinds of behaviors to your JavaScript code. And that's it. Thanks. Man.
So, talking about questions, okay. Where do you get your models and animations from? Do you have a modeler on your team or have sites to recommend?
So yeah, usually the good thing is to find some friend or colleague that does 3D modeling or has got some chops on 3D Studio. There's plenty of people willing to get their models out there. The thing is that what they do, it's just the model, not the UV mapping, which is the hard part. So you cannot texture them correctly, but there's plenty of them. There's blendswap.com for getting models. Yeah, there's a bunch. Depends on exactly if you're looking for something that's got a license or that it's free. So it can be kind of cheapish, but it's free. But I would advise trying to find someone that it's willing to go into a tighter loop of let's do this and we'll get something out that it's cool.
What is the status of ray tracing or particle systems in WebGL and three.js?
So ray tracing is something that won't work on GPUs. I mean, it can be optimized and it can be done really well, but it's like the pure nature of the ray tracing, that recursivity of the algorithm doesn't play well with GPUs that basically try to run everything in parallel, but in a linear fashion. But there's lots of efforts. There's also, I mean, you don't actually have to go all for ray tracing. There's ray marching. Most of the shader toy demos are done with ray marching, which works much better with. It's a similar technique, but it works much better with GPUs. And particle system, basically, since we have GPU particles, I mean, you can have a few million particles running with no problem. Depends on what's the actual movement they want them to have. There's like everyone is doing curly noise, so all these particles that go like this kind of wavy motion. If you want them to do something more complicated, like physical simulation, it's going to reduce. You can probably go to 64,000 particles, which is kind of enough.
So something more general, but I think it's still a good question. Any recommendation on how to start?
Yeah, basically, I mean, there's the 3js.org website. There's a getting started there. There's a ton of examples, and those are like the unit tests of the build. So that's what it's used to check that everything it's working. Of course, it's difficult to unit test graphics. So basically, it has to be done on a visual examination aspect. But yeah, there's a very big community. You can ask on Stack Overflow. So yeah, mostly it's like if you are trying to do something and it makes sense, you will find the solution right away. If you don't find it, it's probably because you're not asking the right thing. You've got mixed up concepts, so someone will probably address you in the right direction.
You recommend to use a CDN for big objects. What about versioning? It is said to be sad for those.
Like versioning, yeah, those are really big files, and some are text-based, so they can be versioned. Some are binary-based, so it depends. Like GitHub now has GitHub is aware of STL files, so they probably have a different path for those, but it's difficult, basically. It's out of space. That's why you're advised to use a CDN or some caching in front of your page, because you might kill your server.
How about performance on mobile?
So everything I've shown works on my Nexus 5, and it's pretty performant. Like and iOS 8 implementations are even faster. So if you're aware of the limitations, which are not usually worrying, like you can have enough performance for mostly what you want to do on the platform. So yeah, I mean it's pretty stable. It's pretty stable, pretty fast, and let me see 1 second. So let's see if I have. Hello. God, send me a signal. Yeah, no, okay, but I can show you afterwards. It's okay. It works. It's really good. Like you should try also mobile WebGL, and like Cardboard, it's using mobile WebGL. So it's a really nice way of getting into mobile WebVR.
Any questions from the audience? Of course there are. Can I get a mic over there?
Sure.
Just a little question. What's your workflow when you have like a ready 3D composition with all the lines, scene, mesh, and material set in, like, let's say Blender or 3ds Max, and then you kind of export it all to and then play with it in a browser, or you follow a different path? Is this more, I guess, related to further referencing the objects on a scene with the JavaScript to provide some additional interactions, I guess. So just wonder, what's your way of doing that?
Definitely. So authoring the assets, it's pretty important on this process. So there's a few ways. If you're using Maya or using 3D Studio, usually it's exported, and there's native importers like the object loader for three.js. Or if you're using Blender, there's an exporter for Blender. But most of the time, there's the loop in which 3D artists work. Then you get that, and sometimes, or most of the times, there's a pre-step you're optimizing your meshes for your renderer. But it's pretty fast, and of course you can do it with Node. You can do execute your script and adapt everything. So the loop it's pretty fast. And then, of course, you can then upload, update, and the designer can see it. So it's a very fluid process, much faster than most of the native tools, actually.
Okay, one more. Can see anyone? No more questions? Okay, there's one over there.
Hello. Are you enjoying playing games, or always looking at the meshes and styles, how they are made?
They've asked me sometimes if I'm aware that I'm building like a game engine. Like that's one of the things. Like everyone's asking about Unity and Unreal Engine. Those are like, of course, are super powerful engines, and they do amazing things. But are mostly first. Our game engine, so everything looks kind of gamey, and every Unity application looks like Unity made, and every Unreal Engine looks Unreal Engine made. And it takes a bit from actually doing something on your own, even though you can code all the shaders. So So it's not that bad. So for production, of course, everyone should go with one of these big tools that do a lot of things. But yeah, there's this cross contamination of the gaming and the real-time graphics. I don't really. I mean, I play games, but I really like more the artistic part of just creating a demo that plays by itself and it's not interactive. I don't know if that's what you were asking.
Awesome. Well, we'll have a coffee break right now. Thank you so much for blowing our minds. Really cool.